The amount of braking the pilot uses has always been of concern. With a tailwheel-type airplane, too much braking could result in a nose-over or ground loop. With large-diameter tires on small wheels, heavy braking could cause the tire to slip on the rim and pull the valve out of the tube. The problem of brake control is still with us, but, today, the reason is different. Modern high-speed jet aircraft usually have more than one wheel on each side, and all of the brakes on one side are controlled with one pedal. With this arrangement, the pilot has no way of knowing when one of these wheels begins to skid. Without prompt corrective action to release a locked-up wheel, the tire is likely to blow out and damage the aircraft, or in severe cases, result in loss of control. Friction created by the brakes reduces the wheel rotation rate, and friction between the tire and the runway slows the aircraft. If the tire rotation slows too rapidly, the tire will begin to slip on the runway instead of gripping it. Once the tire begins to slip, a skid soon develops and braking effectiveness decreases rapidly to near zero. For maximum brake effectiveness, only enough brake pressure should be applied to cause the tire to reach the point where it just begins to slip. This produces the maximum deceleration rate. Maintaining this optimum friction is not easy. As the airplane slows, less brake pressure is needed to maintain the correct balance. Contamination such as water, snow or ice on the runway reduces the coefficient of friction between the tire and the runway. This, too, complicates the problem of maintaining the right amount of brake pressure to achieve maximum braking without excessive tire slippage. We use a simple form of manual anti-skid control when driving on ice. For the most effective stopping, you pump the brakes. They are applied only enough to slow the wheel, then released before the wheel decelerates enough to lock up. This same on-and-off type of operation was employed in some of the early aircraft anti-skid systems. However, this method only works well when the control valves are capable of operating very quickly. When the brakes are applied, the pressure rises until the wheel starts to slip, but not skid, at point A. This is the ideal condition, but the pilot, having no indication that a slip has been reached, continues to increase the force on the brake pedal. Sufficient pressure is soon reached to produce enough friction in the brake to cause the tire to start to skid on the runway, as shown at point B. The wheel now decelerates fast enough to be felt, so the pilot reduces pressure on the pedal. Since the braking force that is needed lessens as the wheel slows, the wheel continues to decelerate even though the brake pressure decreases. At point C, the wheel has completely locked up, and the pressure is still dropping. At point D, the pressure is low enough for the friction between the tire and the runway surface to start the wheel rotating again, and soon after, the brake pressure drops to zero. The wheel then comes back up to speed. A successful anti-skid system requires two features that early on-and-off systems did not have. There must be some form of wheel speed sensor that can detect a change in the rate of deceleration and send a signal for the pressure to be released before the wheel gets deep into a skid. A valve is also needed that acts quickly enough to prevent all of the pressure from being released before the next application of the brake. This controlled amount of retained pressure prevents the brake return system from pulling the pressure plate all of the way back, and allows the brakes to reapply almost immediately. The modern modulated anti-skid system provides the fastest wheel speed recovery and produces the minimum stopping distance on any kind of runway surface. When the pilot wants to stop the aircraft in the shortest distance possible, it is necessary to depress the brake pedals all the way to induce maximum braking. All of the brakes receive the maximum pressure. If any wheel should decelerate at a rate indicating an impending skid, some of the pressure to that brake is dumped into the system return manifold. The control circuit then measures the amount of time required for the wheel to spin back up and applies a slightly reduced pressure to the brake. This reduced pressure is determined by the time required for the spin-up. If this reduced pressure again causes a skid to develop, the cycle is repeated. Some pressure is maintained in the wheel cylinders to prevent the pressure plate from moving all of the way back. This application and release process continues with progressively decreasing pressure until the wheel is held in the slip area, but not allowed to decelerate fast enough to produce a skid. It produces the proper amount of braking for any runway surface condition, with the pilot having only to apply a hard, steady pressure to the brake pedal. When the airplane slows down to approximately 20 miles per hour and there is no further danger of skidding, the anti-skid system automatically deactivates. This gives the pilot full control of the brakes for maneuvering and parking. As with most auxiliary systems in modern aircraft, the anti-skid systems have built-in test circuits, and may be deactivated in the event of a malfunction to give the pilot normal braking but no anti-skid protection. Many large jet transports have an auto-brake feature that works in conjunction with the anti-skid system. When the system senses weight on the main wheels, it automatically applies the brakes to produce one of several pilot-selected levels of deceleration. This results in a more immediate application of the wheel brakes and maximizes the use of the anti-skid system. The pilot can override and disarm the auto-brake system by applying manual brakes. There are various designs of anti-skid systems. Most contain three main types of components: wheel speed sensors, anti-skid control valves, and a control unit. These units work together without human interference. Some anti-skid systems provide complete automatic braking. The pilot needs only to turn on the auto brake system, and the anti-skid components slow the aircraft without pedal input. Ground safety switches are wired into the circuitry for anti-skid and auto brake systems. Wheel speed sensors are located on each wheel equipped with a brake assembly. Each brake also has its own anti-skid control valve. Typically, a single control box contains the anti-skid comparative circuitry for all of the brakes on the aircraft. Wheel speed sensors are transducers. They may be alternating current or direct current. The typical AC wheel speed sensor has a stator mounted in the wheel axle. A coil around it is connected to a controlled DC source so that when energized, the stator becomes an electromagnet. A rotor that turns inside the stator is connected to the rotating wheel hub assembly through a drive coupling so that it rotates at the speed of the wheel. Lobes on the rotor and stator cause the distance between the two components to constantly change during rotation. This alters the magnetic coupling or reluctance between the rotor and stator. As the electromagnetic field changes, a variable frequency AC is induced in the stator coil. The frequency is directly proportional to the speed of rotation of the wheel. The AC signal is fed to the control unit for processing. A DC wheel speed sensor is similar, except that a DC is produced the magnitude of which is directly proportional to wheel speed. The control unit has three main functions: to generate electrical signals usable by the control valve, to regulate brake pressure to prevent a skid during landing deceleration, and to prevent application of brake pressure prior to touchdown. Before the airplane touches down, the locked wheel detector sends a signal into the amplifier, which causes the control valve to open the passage between the brakes and the system return manifold. This prevents the pilot from landing with the brakes applied. As soon as the airplane touches down, the squat switch registers that weight is on the wheels. The wheels start to spin up, and at approximately 20 miles per hour, generates enough voltage in the wheel speed sensor to signal the locked wheel detector. The detector then removes the touchdown control signal from the amplifier. This allows the control valve to apply full pressure to the brakes. When the airplane is on the ground and the wheels are rotating at more than 20 miles per hour, the skid detector and modulator provide almost all of the anti-skid control. A deceleration threshold is designed into the skid detector circuit. The reference normally is set to about 20 feet per second, with a wheel speed that is at least 6 mph below the speed of the airplane. When a wheel decelerates at a rate greater than this threshold value, the skid detector signals the amplifier and then the control valve to reduce the brake pressure. It also signals the modulator, which automatically establishes the amount of current that will continue to flow through the valve after the wheel has recovered from the skid. When the amplifier receives its signal from the modulator, it maintains this current, which is just enough to position the flapper to prevent the pressure from being completely released. The applied current maintains a pressure slightly less than that which caused the skid. A timer circuit in the modulator then allows this pressure to increase slowly until another skid starts to occur, repeating the cycle. When the aircraft is on a wet or icy runway, the anti-skid system holds the wheels in the slip region. However, the locked wheel detector activates whenever one wheel hydroplanes or hits ice and slows down to less than 10 miles per hour, while its mated reference wheel still rotates faster than 20 miles per hour. A timer measures the duration of the skid detector signal. If it is more than 1/10 of a second, it sends a full dump signal that holds the valve in the full dump position until the wheel spins back up above 10 miles per hour. When all of the wheels are turning at less than 20 miles per hour, the locked wheel arming circuit disarms, giving the pilot full braking action for low-speed taxiing and parking. The control unit for anti-skid systems using AC sensors operates in the same way as those using DC generators, the only difference being the addition of a converter circuit. This circuit receives the varying frequency alternating current and converts it into a varying voltage of direct current. The changes in the DC voltage exactly follow the frequency changes of the AC. A 3-port anti-skid control valve is located in the pressure line between the brake valve and the brake cylinder, with the third line connecting the control valve to the system return manifold. During normal operation of the brakes, with no indication of a skid, the valve serves only as a passage and allows the brake fluid to flow into and out of the brake. When a wheel begins to decelerate fast enough to cause a skid, the control unit detects the changing output voltage of the wheel speed sensor. The control unit sends a DC signal to the control valve, which closes off the pressure port and opens the passage between the brake and the system return. This rapidly operating valve maintains an output pressure that is directly proportional to the amount of signal current from the control unit. The DC signal from the control unit flows through a coil around the armature of the flapper valve. This armature is free to pivot and is centered between two permanent magnets. When the signal from the control unit indicates that no skid is impending, and the braking action should be normal, the magnetic field of the coil reacts with the fields of the permanent magnets and holds the flapper centered between the nozzles. Fluid from the brake valve flows through the filter and discharges equally from each nozzle. Since the amount of flow is the same through each orifice, the pressure drop across the orifices will be the same, and the second stage spool valve will assume a position that allows free passage between the brake valve and the brake. When the control unit receives a signal from the wheel speed sensor indicating an impending skid, it sends current through the coil of the armature to polarize it. This causes the flapper to pivot and unbalance the flow from the nozzles. The flapper moves over, restricting the flow from the left nozzle and opening the flow from the one on the right. There is now more flow through orifice 2 and therefore a greater pressure drops across it, leaving pressure 1 greater than pressure 2. This imbalance of pressures moves the second stage spool over, shutting off the flow of fluid from the brake valve to the brake, and opening a passage from the brake to the return manifold. The extremely fast reaction time of this valve allows it to maintain a pressure at the brake that is directly proportional to the amount of current flowing in the armature coil. Thanks for watching.